Okay, so I made the claim earlier that power series were easy to differentiate and integrate, so let's address this idea. So differentiation and integration of power series. We're going to encompass the ideas into a theorem, so differentiation and integration of power series. Theorem. If a power series sum and goes from 0 to infinity, Cn x minus a to the n, has radius of convergence r 1. The function defined by f of x equals this power series. So remember, each power series is going to describe a function. So the function defined by this power series, which is c0 plus c1 x minus a plus c2 x minus a squared, and so on, is differentiable and hence continuous, if you remember our Calc 1, and therefore continuous on the open interval a minus r to a plus r. And furthermore, we can give a formula for it. F prime x is equal to, well, n times cn x minus a to the n minus 1, from 0 to infinity. And this is exactly what we would get if we just naively differentiated each term. So the c0 would disappear, the c1 would just, the c1 x minus a would become c1, etc. So this is the formula for the derivative of the power series on the interval where it converges. Secondly, for absolute value of x minus a less than r, assuming you still have this radius convergence r, the integral f of x dx is equal to some constant c plus c0 x minus a plus c1 x minus a squared over 2 plus ... so on. Okay, which, if we summarize into the series notation, is this constant of integration c plus sum cn x minus a to the n plus 1 over n plus 1, where n goes from 0 to infinity. So NB, these two series for f prime and f of x integrated, the antiderivative, both have radius of convergence r. However, the interval of convergence may change, as you may lose the endpoints. So it may change at the endpoints. So for absolute value of x minus a equal to r. So again, you have to check these, even for the derivative and the antiderivative, you have to check these individually.